Okay, so I hope you are able to see my screen. Can anybody confirm that, please?
Yes, sir.
Okay, and you're able to see me and hear me also.
Yes, sir.
Okay, all right. So, before I had the network issue, I believe we were talking about uh, SIG action in the last lecture, and basically, um, the SIG action is the system call that is provided to us to allow multiple masking of the signals within the signal handler, right? So you set up a signal handler for one signal, which is the number that we provide in the SIG action. Now the SIG action structure accepts the function pointer, which is the handler pointer, right? So again, you could have three different values depending on what you want to do. You want to either set a default action, you want to ignore the signal, or you want the customized function, right, that you want to use as a signal handler. So any one of these three values, again, you can provide in the SA handler. And then SA mask is the is the member of the structure where you can provide set of signals, right? Set of additional signals that you want to block. So it means that whatever signal numbers you provide as a set of the set of the signals, those are the signals that will be blocked. Now, how do you create this set of signals? Using this macros or functions provided by the operating system, right? So you can have an empty set by using this function, which will create the set but without any member in it. You can use sigfill set, which will basically allow you to use all the signals that are available in the system and put that in a set, right? You want to add any particular one signal, then you can use the sig add set, or delete a signal, or you want to check whether a particular signal is part of the set or not. Is it a member of the set or not, right? Then you can use this particular macro. So these set of functions are provided to us by the operating system that will allow us to create the set of all signals, right? Or whatever number of signals we want to block using SIG actions. So once you have created this set, then you can provide this particular variable as the third member of the structure, and then you can provide that structure pointer here. That will be basically used by the SIG action system call. Okay, so we'll just take a couple of more slides here for the signals, and one of the other things that we want to do, let's say for example, here SIG action is allowing you to set the handler, and in addition it allows you to mask the other signals. But let us say that you already have the handler, and when you are setting up the signal handler, you don't know which signals you want to block, right? So at the time of using SIG action function, you don't know what all signals to be blocked. So instead of using SIG action, maybe you can just use a signal and you can provide a new handler there, right? And then within the handler, you can actually create a set using this function, and you can actually mask those signals which are part of the set, for which this special function, again system call, is provided to us, which is called sig proc mask. So what is the function of sig proc mask? Sig proc mask basically says that at the time of setting up the handler, if you don't know which signals you want to block, but within the signal handler you want to block a set of signals, then you can create a set using these functions first, and then you can provide that set over here in the sig proc mask, and you can provide the action over here, right? So how is sort of like an action. This is the set that you want to block, and this is the previous set which was already blocked, right? So this is the old set of old set of blocked signals will be returned to you, and the new set of signals that will be blocked that we provide here, right? The how has three values. One says block, right? Sig underscore block. What it means is that whatever the current number of signals that are already blocked, in addition to that, right? So you add to that set, you would be adding this new set of signals, right? So whatever is the current block signals which are there, you are adding a new set of signals to that set, right? So there will be more number of signals now that will be blocked. That is what you can do using the block action or how. Unblock is similar. Instead of doing the blocking, you are basically doing the unblocking. So whatever the current signals that are blocked, out of which you will be removing some of the signals that you don't want to block. Right. So that is what the unblock will do. And the set mask is basically what you are going to do is whatever the number of current signals that are blocked, you don't care about that. You reset that. Okay, so you reset that and you just provide a new set, completely new set of signals, right? So basically block and unblock works like a relative blocking. So it considers the existing set of block signals or unblock signals, and it will basically perform the blocking and unblocking to the existing set. But when you use the set mask, it basically works like an absolute setting, absolute masking, right? Meaning that no matter what the old set was, you want to basically use the new set of signals, right? Which is going to be the only set that will be blocked. Okay, so this is another function that is provided to us in case if you don't want to do the masking using the sig action in the as a mask field, right? So you can actually use this signal function to to provide the customized handler, and then in that customized handler you can use this set of signal to to block within that, right? So that is something also possible. So I've just given an example over here for the sig proc mask. So in this case, we have the int handler, which is set using the signal function. And then within the int handler, we are forming, the set with the first we are forming the empty set, and then I'm just adding one more signal, right? But you can use the fill set also over here. It doesn't matter. And then you can use the sig proc mask. That will, that will basically block this secret signal. And then you can, at the end of the handler, again you can use the sig proc mask, and you can use whatever the old set that was returned to you by the sig proc mask to again set the mask for that one, right? So this is the example that you can do. Instead of blocking individual signals at a time, you can block set of signals all at once, right? So that is an example that is showing you here. And then second example that I wanted to show you was using the sig action, right? So in the sig action, you can see that we are using the sig fill set as the as the function, which means that it is going to be blocking all the signals, right? All the signals, because the sig fill set will give you all the signals. So you block all the signals, and then for each of the each of the signal number that we have 1 to 31, except for sig kill and sig stop, except for sig kill and sig stop, you are going to be setting up your new handler. And in the new handler, you will be setting up not only the function, but you are also going to be setting the mask for the signals, right? So again, just an example that I wanted to show you about sig action. So this is how you can use the sig action, and this is how you can use the sig proc mask. Okay, so I think these 3-4 slides were left when we finish up the last lecture, because I had some network issue. So so this is all about signals. So, and this is where I would stop about the signals. Any questions on the signals that we can address here? Any questions? Okay. So if there are no questions with this particular topic, I'll move on to the next topic, which is basically the concurrent programming, right? So concurrent programming is the new topic that we'll be covering. And what is a concurrent programming? So I think I have briefly mentioned earlier about the difference between parallelism and concurrency. So the idea basically is that you want to perform certain tasks in parallel, right? Either you want to run multiple applications in parallel, or maybe you want to perform certain operations in parallel within the same application or something like that, right? So that is basically what we call concurrent programming. Now the point is, why do we need concurrent programming, right? So what is the reason, right? For example, till 1990s, I think early 1990s, the computers only had a single processor, single core machine, a single processor machine. So it cannot perform, it cannot execute multiple applications at the same time unless you are doing context switching, or it would not be able to perform multi-threading kind of operation. But nowadays, all of our computers have multiple cores in them. So even your desktop would have, probably 4 cores, 6 cores, 8 cores. And if you go higher up in the server ranges, then you have 12, 24, 36 cores also sometimes, right? So basic idea is that how do we take an advantage of these many processors we have? So there are two types of applications. Okay, there are two types of applications that are, that can take an advantage of this architecture. So one type of application is what we call computationally intensive application. Okay, so what is a computationally intensive application? Basically, what it means is that it requires more amount of computation, okay, than the data access. Okay, or similar type of computation on each of the data that is accessed from the memory. So an example could be that, let's say you have a large array, right? Let's say 1 lakh elements in an array, and you want to do the summation for all the elements in an array. Okay, so this could be something that can be this task can be divided. For example, if your computer has 4 cores, then you can take 25,000 elements from each of this 1 lakh element, so you can divide that 1 lakh into 25,000 set each, and then you can send each core 25,000 elements, and each core can actually do the summation of 25,000. And then once you have those 4 different values, subtotals, then you can take maybe 1 or 2 more cores, and then you can do subtotals. You can do addition of those subtotals and get the final result, right? Second example could be that, let's say you want to convert your image from RGB image to grayscale image. So what happens is that each pixel has RGB values, right? So this is your matrix, this is your two-dimensional array, right? Which is your the row will be the size of the image, which is the number of pixels, and then you could have or actually width will be the RGB values, and the length and the depth will be the RGB values, and length and the width will be the size of the image, right? So whatever number of pixels you have, right? Let's say 1024 by 728. Let's say that pixels you have, so that is what you have. Now you have to apply this formula for each of those pixels RGB values. Now this task can be parallelized, right? Because there is no dependency of applying this formula for different values of RGB for each of the pixels. So you can have, let's say, like I said, if you have 1000 pixels and if you have 4 cores, each core can take 250 pixels values, RGB values, and it can apply this formula on each of those 250 different sets. So this is what we call computational intensive application. The other type of application that can take an advantage of concurrent programming is IO bound application or memory bound application, meaning that it requires a lot of memory access compared to the computation, or IO access compared to the computation. So for example, your databases, right, where you run the query, and the query, single query may require large amount of data to be accessed from the disk. Now you don't want your database process to get hooked onto a particular core, because the core will be mostly waiting for the database application to get data from the disk, because disks are always slower. So instead of keeping the core with the particular database process, you can assign that code to somebody else, to some other application which is ready to run, right? So again, you can use the you can use the concurrency in terms of context switching or running multiple applications together in case of memory bound or IO bound application. But if the task is larger, there's a lot of computation required, the task can be broken down into a smaller pieces, and then that task can be executed on multiple cores. So these two types of application can take an advantage of concurrent programming, right? Now, how do we implement, right? How do we implement concurrent programming? So one type we have already seen, which is what we call multi-process programming, in which we use the fork and create the parent-child model, right? And so you divide the logic in your code so that the parent process does something, child process does something else, and both the parent and the child processes are allocated to different cores, right? And if they are allocated to different cores, that means that they are performing whatever task that needs to be performed parallelly or concurrently, right? Another method you can use is multi-threading, right? So multi-processing environment we have already studied. Multi-threading environment is what we are going to cover in this chapter, right? So that is why I'm covering this in a bit detail, because multi-threading is different than multi-processing, and how it is different, why it is different, what are the advantages, disadvantages, that is what we will cover in this chapter, right? So multi-threading is another programming environment where you can create small pieces of code which can actually run on different cores, right? So that is something that again you can do using multi-threading environment. Now you could have a computer which has multiple cores, where you can actually use multiple process or multiple threads. However, there could be another type of architecture where you have the computers connected via network, right? And that is what we call distributed memory architecture, because the memory is not shared between the computers. So let me actually show you the diagram which makes sense. So this is the kind of computer that we have available today. This is where this is the early 90s and older time than that, right? So in 60s, 70s, 80s, 90s, I think 65 onwards, this is the type of computers that were there. And then from then onwards, we get the computers in this model, right? So you have a processor or a CPU, and then it has multiple cores in them, and then each of the cores can perform or run different processes or different threads, and then you have a common memory. So the data and the code that you want to share between the multiple processes or multiple threads can be shared using the shared memory. Okay, this is the third type of architecture which generally is used by cloud infrastructure and stuff like that. So let's say you have a server which has the multiple cores, and then it has its own memory. There's another server which also has its own processor and memory, and then they are connected via network, right? So for example, when you ask for the cloud server and you ask for a contingency, so basically you say that my data should never get lost. What the cloud provider will have to do, let's say your data is housed over here in this server, right? But then there will be a backup server that will be kept in a different region, right? So for example, you bought a server in let's say India, there will be another server, let's say in Singapore, right, which is keeping also your data as a backup, right? And this replication, right, the constant replication will be going on between the two servers, to make sure that in case if this server goes down, you have your data and everything else in your backup server. Okay, so this is the kind of environment that can also be used, which is basically what is called distributed memory system or distributed computing environment, right? So this kind of environment cannot use multi-threading. Okay, it can only use multi-processing or multiple applications on two different servers. But in this kind of environment, we can use multiprocessing as well as multiple threads. Okay. Uh, Now, what is the difference between the how the communication actually, right? So how do we do the interaction between the concurrent tasks? Meaning, let's say you have multiple process or multiple threads. How do you communicate between them? Whether you are in a shared memory architecture environment or you are in a distributed memory architecture environment. So if you are in a shared memory architecture environment, which is this one, it is very simple because we know that the data area can be shared among multiple cores, right? Each of the core, right, has access to the same memory. So if I make a change to one particular variable in this memory, that change can be available to each of the cores, right? However, in case of distributed memory system, the problem is if I make a change to a data area here, that change is not available in this memory. Okay, so the only way we can do we can interact between the two processes here is by sending a message, right? So that's why the distributed memory system always has to depend on the message passing interface, right? So there is a message passing interface MPI, which is what is normally used to communicate between the two processes which are running on the distributed memory system. Okay, so that is basically what we are seeing here, that all the tasks can have the access to the same physical memory, and therefore by changing the content in the memory, the data can be shared among the multiple processes. Whereas here we don't have a common physical memory, so the only way the communication can take place is by exchanging the messages. Any questions so far? Okay. Now let us look at what is the advantage of using what is the advantage of using the serial process versus the parallel process or parallel task, right? Uh, the serial process basically is, let's say that you have eight different values, right? You have eight different values and you want to do the summation of that. So let's assume this is an array and you are going to do the summation of this one. How it is going to work? You're basically going to most likely run a loop, right? You're most likely going to run a loop. So in each loop iteration, it's going to be doing the addition of just one additional value, right? So you have, let's say you start off with two, but then after you get the sum of this one, then you take in the third one, then you take in the fourth one, right? So you keep on adding the one more element each time. So which means that when you use the sequential operation or serial operation, right, it's going to take n steps for adding n different values, right? N steps for adding n different values. However, when you go into the parallel task, right? So let us consider this as a parallel task. What does this mean? Right? So here what we can do is, since we have four cores in the system, let's assume that we have four cores in the system. What we can do is we can allocate, right, two values each to each of the cores. So you get core 1 which gets x1 x2, core 2 gets x3 x4, core 3 gets x5 x6 and so on, right? So first time you get the parallelism four ways, four times. Okay, so you get four times the parallelism because each of the core can do addition of two numbers, and then you get the intermediate result. Now, in the second step though, even though we have four cores available, we can only use two cores out of which, because you only have four values that can be added, which are the subtotals. So you can then have A and B given to core 1 and C and D given to core 2, and then you can do the summation there. So even though you have 4 cores, you can only use 2 of them. Okay, and then finally, again, you can just use the last summation. So I mean, for the last summation, you can only use 1 core. So in essence, what I'm trying to say is that even though you have 4 cores, the 4 cores can be used only during the first operation, right? And then the second step and the third step, you have to use less number of cores because of the dependency of the data or the task, right? So this task has to be performed before this task can be done, and this task has to be performed only after this task is done. So there has to be at least 3 steps, right? There has to be 3 steps when you have 8 different values. And the answer why this 3 came, because it is basically logarithmic of 8, right? So you are basically using this method, in a tree kind of formation. So this is your root, and then this is your second step, third step, and so this is basically your log of 8 or log of n becomes the number of steps in case of parallel task whenever you have this summation, right? So this log of n answer is for the addition of the numbers. The different algorithm, different solution may have different runtime, right? So you have to calculate this runtime differently for each of the different problem, right? When you do the parallelism. Okay, now the point is, whenever we do any operation using the serial algorithm, right? So we call that time taken by the serial algorithm as TS, and the time taken by the parallel algorithm as TP, right? And you have the number of processor SP. So the parallel version of the algorithm ideally is supposed to take, so let's say that you have TS is 8 steps, right? And the number of processors is 4. So ideally, your parallel time should be 8 divided by 4, which is only 2, right? Which is only 2. So you should get TPS 2. But in reality, if you see, our TP is 3, right? Why? Because there is a task interdependency, right? So there is a task interdependency, and because of which the time taken is higher. Now, another concept that is there, which is called speed up, and the speed up concept basically says that TS divided by TP, right? So this value should be 4, right? Because your TS is 8, your TP is 2, and when you do this, it should be equal to 4. So it should be equal to the number of processors or number of cores we have, right? So ideally, if you are able to parallelize everything, then the number of processors will be equal to the same thing as speed up. But in reality, again, that is not the case, because if you look at it, number of steps required for the serial algorithm is 8, number of steps required for the parallel algorithm is 3. So if you do 8 divided by 3, we get 2.67. Ideally, this number should have been 4. So ideally, this number should have been 4, but it is 2.67. The reason being that there is a task interdependency. Okay. Furthermore, when you do the parallelism, right, of the algorithm, many times what happens is that you have to send large amount of data between the cores or between the computers if you are using distributed network, right? So in that case, it takes time to actually send the data. So let's say if you have 4 cores, and if you are trying to do the addition of 1 lakh element, then each core should get 25,000 elements. So reading that 25,000 element, right, is going to take time. Okay, and that is another cost that you have to add to your parallelism. Okay, so these are the two important reason because of which we do not get the speed up same as the as what we normally expect, right? The default speed up that we expect, which is the number of processors. Okay, Now we are going to talk about the difference between the multi-process environment and multi-threading environment, right? So what is the multi-process environment, which we have already seen, right? So you have a process, right? Now by default, whenever you create a process, there is also a default thread that is created. Okay, there is also a default thread that is created. Okay. However, let us assume that this is my process. Now, process obviously has a code area, the data area, the open files area. So this is your open process wide file open table. You have the processor registers, and then you have the stack, which is where your local variables of the functions will be stored, or the parameters that you're passing to the functions will be stored, right? So this data area is your heap area, what is called heap area, or a global data area. This is where your global variables will be stored, right? Or any dynamically allocated variables will be stored. Okay, so this is my process, right? And this process is running a default thread inside it. Now this process is doing fork. Okay, so this process, when it does fork, you come to this picture, right? You come to this picture. So what are you doing? So when this process is doing fork, it is creating a completely new process, which is we have termed that as a child process. So this becomes my parent process, and this becomes my child process. So my parent process has the same code area, which is duplicated for the child process. Even the data area is duplicated, the open files are duplicated, the registers are duplicated, the stack is duplicated. So each and every component, each and every memory area that a particular process requires is duplicated when you issue the fork system call in the multi-process environment. So this is my parent process, this is my child process. Now, let us say that instead of doing fork, this particular process has this default thread which is running, right? And this thread is creating another thread. So now instead of creating different process, I'm creating a new thread, a child thread. So this is my main thread, and now I'm going to create a child thread. So when I create a child thread, I actually come to this picture. And why this picture? And you can see the difference between this one and this one. The major difference between multi-threaded environment and multi-process environment is over here. So when you create multiple threads, you don't duplicate code area, you don't duplicate your global data area, and you don't duplicate open files. All of this stuff is shared between multiple threads. Okay, so which means that is why the threads are called a lightweight process, because when you create a thread, the only new thing that has to happen is create a new stack and assign a different core with the different status registers for the processor, right? So process status word will be the new, and the stack will be new, because stack is used for the local variables, and this thread will have a different set of local variables compared to this thread. So this thread will have its own local variables, this thread will have its own local variables. Okay, but the global variables are shared among all the threads, the open files are shared among all the threads, and also the code is shared among all the threads. So this is the major difference between the multi-threading environment and the multi-process environment. Okay. Now, when we come to this picture, it is obviously the combination of this one and this one, right? So you have multiple processes that are created, and then within each process also you can create multiple threads. So, for example, a parent process can have multiple threads. The child process also can have multiple threads in that, right? So this is how the multi-process versus multi-thread environment works. Any questions? Again, this topic is very important for you to understand. If you don't understand this topic, it will be very difficult to understand anything further in this chapter. Okay. All right. So the point is, when you are in the multi-process environment, right? Why it is called a heavyweight process? Because first of all, you need to create a new process control block. You need to allocate a new memory address spaces for code, for data, for global data, and for open files. All of that, right? So new memory allocation has to be done. New process control block has to be created. Possibly a code, right? Code that you want to run. Maybe you want to run a different program into the child process. So that code has to be also loaded if you do exec, right? So that is something that also has to be done. And then a scheduler will have to use PCB to run that process. So these are the, sort of like a heavy duty steps or fat steps that the operating system has to perform for the new process when it is created. Whereas in case of threading, thread actually runs as part of the same process. So therefore, there is no need to create PCB. There is no need to allocate memory for global data area and the code and the open files. All of that is shared, right? The only additional thing that the operating system has to do is allocate the memory for stack, for a new stack. Okay, so once it creates a new stack and once you have the new process status word for that particular thread, then you have a new thread. And the scheduling, right, the scheduling is performed on the thread basis, right, per thread basis, meaning that each thread is allocated to a different core. In this case, each process is allocated to a different core. So therefore, thread model is called a fine grain model. Fine grain model, right? Fine grain scheduling model, because the scheduling does not require a lot of switching over, right? Code remains the same, data remains the same, files remains the same. So let's say one core is using this thread, and then the same core is allocated this thread, then this thread requires the same code area, same data area, same open files. So therefore, there is no need to do context switching for these three things. Only context switching needs to be done is for the stack, and that's about it, and the registers. That's about it. Okay, this is the reason the thread are called lightweight processes, and our normal process is called heavyweight process, right? So heavyweight process and lightweight process. What is the advantage of thread versus the process? So obviously, as I said, it is much quicker to create the thread because it doesn't require these steps, right? It doesn't require duplication of code data and files area. Only thing it requires is the new stack. That's it. And the CPU state. That's it. Right. It is also much quicker to do the context switching between the threads. Right. Because of the same reason. So context switching becomes the faster. Creation of the thread becomes the faster. And the third advantage is that it can easily share the data also. Why? Because again, if you look at the data area, the global data area is same for all the three threads, right? Whereas if you look at here, once this data area is copied over here, any change that you make to this data area is not available over here. So sharing of the data between the multiple processes becomes difficult. This is the reason we use pipe, right, to share the data, right? But in case of threads, multiple threads, we don't really need to do that. You can always share the same data using the global data area. What is the disadvantage though, right? So obviously there is some disadvantage. The disadvantage is that processes are more flexible because it has different memory maps. So each of the process has its own memory, so therefore they become a little bit more flexible. Okay. There is a security concern between the threads. What is the security concern? The security concern is that once one thread is stormed on the data, meaning that one thread corrupts the data, that corrupted data is also applicable to all the threads, because again, like I said, the data area is shared between all the threads. So let's assume that this thread has corrupted the data area somehow, right? So that corrupted data is also applicable to these two threads, right? These two threads are not going to get a fresh copy of a data, right? So therefore, this data, once corrupted by any of these three threads, then the other threads also will be suffering, with that corruption. And then the third one is talking about the user level thread and the kernel level thread, which I'll come to that in the next couple of slides. Any questions? See, my point is, this part of understanding the multiple process and multiple thread is very important. The reason being that, when in case if you happen to work in this area, where you have to use these concepts, it is very important to understand whether to use a multiple process or whether to use multiple threads, and which which of the two will give you an advantage in a particular situation. So that is why always it is important to understand the difference and how to use them, right? So the types of threads, we basically have two types of threads. One is the user level threads. So what is the meaning of user level threads? User level threads means that only the user application, the process, right? The user process is only aware of multiple threads, meaning that the creation of the threads, termination of the threads, maintenance of the threads, what kind of code will run as part of the threads, all of this has to be managed in the user application. So the kernel application, the kernel space has no idea that there are threads running inside the process. So this is one process, and there may be multiple threads within that process, but then the kernel is absolutely unaware of the threads. So the disadvantage of this method is that the problem is that because the kernel is not aware of the threads, you cannot actually allocate a thread to a particular code. Okay, so the kernel will be allocating the code to the process only. Now within the process, if you have multiple threads, that particular process can say which of the thread will be allocated to that code. But because kernel does not know that there are multiple threads, kernel will not be able to allocate a thread to a particular code. Okay, so again, context switching can be done to improve the parallelism or to improve the performance of the process, but all of that has to be managed within the application process and not in the kernel operating system. Okay, so this is one of the biggest disadvantage of user level threads, and this is one of the reason user level threads are rarely used. Okay, user level threads are rarely used. However, there is an advantage that you have the application process is aware of the threading, so the switching is a bit easier because process does not have to inform the kernel that you switch the code to a different threads, right? It is managed only within the process. Second advantage is that because the code is within the application, application process or application code, if this application code can be recompiled for another operating system, then the same code, same ULT code will work in another operating system also. So let's say this process is running in Linux, but then if you can compile this code for Windows, then this code can also apply, multiple threading in Windows environment. Okay, so that is the advantage of the ULT. But not able to allocate thread to a core for parallelism is a huge disadvantage, and therefore ULT is very rarely used, as I mentioned. The second type of threads that you have is the kernel level threads. So as the name says, user just says that I want to create a thread, right? and it just offloads. It basically calls a system call of the kernel, and kernel will take care of creation of the thread, management of the thread, which code will be executed as part of the thread, and everything. So kernel is fully aware of how many threads are there and which thread belongs to which process. All of that is is known to kernel. So the advantage, most important advantage to the kernel, as you can see, is that it keeps track of the number of processes, and within each processes, what are the threads that it has. And then because kernel is also aware of the number of threads or all the threads, it can allocate a thread to a core. Okay, so instead of allocating process only to a core, it can also allocate a thread to a core. So parallelism can be further improved by allocating different threads to different cores. That is an advantage, right? Disadvantage is that, uh, as I said, heavy thread switching involve the mode. So basically, let's say you have, like, let's say you create 100 threads, right? So that means kernel will have to switch each thread very fast, because all the 100 threads has to be given some time of the process. So context switching will have to happen very quickly, and this is the disadvantage of the kernel threads if you have many threads in your system. If you have a small number of threads in your system, then you're fine, right? Then kernel level thread actually works much better. And as I mentioned, this is one of the reason kernel level threads are most widely used. Okay, so kernel level threads are the ones which are in use most of the time. And what we are going to learn in this chapter, the POSIX threads. POSIX threads are the kernel level threads, and that is generally used by all the operating system, well-known operating system. So that is what we are going to study. Okay. There is a third category which actually combines both levels. Okay, it combines both levels, the user level thread as well as the kernel level threads. So there will be some functionality implemented in the user application, but then there will be this functionality will be taking an advantage of the kernel level threads also. Now the question is, where would it use this? Okay, if you have studied Java, okay, if you have not studied Java, then don't worry about it. But just for your knowledge, Java has a tool called JVM, which basically runs the Java code, right? So the tool JVM, which runs the Java code, actually implements the user level threads. But then inside the JVM, it also takes the help of the kernel level threads. So the Java application or JVM tool is a perfect example of using the combination of user level threads and the kernel level threads. Okay, so that is an application that combines both. But other than that, I think most of the threading environment that you would look at will be using the kernel level threads, and that is what we will be studying. Any questions from anyone? Are you guys there, or am I just talking to a screen?
Yes, sir, we are here.
Okay, thank you. All right. So now we whatever we learn, this is all theory that I talked about, right? All these 13 slides were theory, just to give you an idea about what the threads are. Okay, but obviously for this course, as you know, we don't learn anything without practice, right? We always look at an example, we always look at the code and see how it works. So what we are going to do is we are going to use a library which implements the POSIX threads. So POSIX threads are the threads that are used by many well-known operating systems, right? So FreeBSD, NetBSD, OpenBSD, Linux, Mac OS, Android, Solaris, DOS, Microsoft Windows, right? Most of these applications, all of these applications uses POSIX threads, and in short we call it as P threads. Okay, so this is the library file that provides us the functionality of P threads, and this is what needs to be linked with your C code whenever you implement any functions from the POSIX threads. This is the header file, pthread h header file, and let me start the VirtualBox. So when you locate libpthread.a, so there is a static library file in this location, right, which you can use, or you can use the dynamic library file, which is also available at that location, right? So you can see that the libp thread is available in both flavors, static library as well as the dynamic library. Now obviously when you compile using GCC, by default it will link first the dynamic library. If you want to link the static library, then you have to use that, minus capital dot option, and then you have to give the path to this static library. Okay, but anyway, we'll basically use whatever library GCC links with. Okay, so what are the functions that are implemented in this library file? So there are generally four types of functions. So you have a thread management functions which will allow you to create threads and so on. It will use mutexes. It can use the conditional variables. It can use the synchronization between the threads using the locks and semaphores, right? So four types of functionalities are there. We are going to use most of this functionality throughout this chapter. Okay. So as I said again, you can link this libp thread using the minus L switch, but GCC provides a special switch called minus P thread to link that library without using minus L option. So if you do man GCC, and then if you search on minus P thread, you can see that in the linker option, it says that minus P thread is one of the options that you can use. Okay, so this option will allow you to link that libp thread library by default. Okay, that is what the GCC will allow you to do. So that is what we are going to use. Now, first of all, as I mentioned, that the process is different, and it is basically sort of like an envelope on top of the thread. Okay, so process is basically a fed thing, right? It has code, data, file open file stack, and all that stuff. Thread is something which is within the process, running within the process. So when you look at the process, it has a different process ID. It will have an ID of its own. Even the thread has its own ID. Why? Because see, if you look at this, if you look at this picture, one process can have multiple threads. So you should also have the identifier for each of the thread, right? So there has to be an identifier for each of the thread. So therefore, each of the thread will also have its own ID. And to read that ID, to get that ID, you have to use this function. Okay, so pthread underscore self will return you the thread ID number. it will return you the thread ID number. Okay, and that number will be different from the process ID. So you can see that in my main function, I just have one line here. I'm just using get PID, which will give me the process ID of this process, and then I'm using the pthread self, which is going to give me the thread ID of the thread. So why I'm doing this? Because I wanted to show you that this particular picture, right? This is a process, but then there is also a thread, the default thread running inside that process. So I'm going to get the process ID also, and I'm going to get the thread ID also, right? In this code. So that is what I'm going to run. So pthread self is the code. So I'm going to compile that minus pthread pthread self example minus o pthread self example out, and then I'm going to run that code, and you can see these two different values. So process ID is 2982 and the thread ID is this, right? So this is the big number, which is the thread ID number, and this thread is the default thread which is running in the process 2982. Okay, and every time when I run this code again, you will see that the number will change. So this process ID will obviously will change, and then also the thread ID will change. Press something which created this thing. Now, this is the default thread that we talked about. Now we are going to talk about the thread creation, right? So we say that when you have a process, the default thread is running like this, but then within the process you can also create more threads, right? So let's assume that this is the default thread, but then I want to create one more thread. So how do we do that? So for that we have to use pthread create function. So pthread create is the function, right? That will be used, or system call that will be used, that will create a new thread. So this is my thread ID that will be returned by the operating system. So first parameter is actually a return value, okay, and this is the thread ID that will be returned to me. That is the new thread which is created. Now second argument here is the attribute that I want to pass to the operating system for a specific thread. Now, generally speaking, we don't pass any attribute for creating a new thread. So we would generally pass a null value here. But for example, what could you pass over here? We know that whenever you create a thread, there is a new stack that has to be allocated. Now, by default, operating system use a particular size of the stack. So let's say it may allocate, let's say 2 kilobyte of memory for a stack for the new thread, or 4 kilobyte, depending on what is the setting in the operating system. But let's say that you know that in this thread, you are going to use a lot of local variables. So 2K value of stack is not enough. 2K size of the stack is not enough, and you want to allocate bigger size for the stack. So that information can be passed using the attribute parameter. Okay. Third parameter here is the function pointer, which is the function that will start the thread. Right. So basically, whenever you start the thread, some code has to be executed. Like in case of process, we had this if else statement that indicated which code will start a process. Whereas in case of thread, there is a function. So this function will basically the starting function for that thread. Okay, so that's why we have to provide a function pointer. So function pointer is the function which will actually start the thread. Now this function may require some argument to be passed, which can be passed using this fourth parameter. Okay, So this function cannot be passed arguments like we normally do in normal functions, right? Because this is a special function used by a new thread. You cannot actually pass the parameter here. You have to pass the parameter to that function using this fourth argument. And how it is done, I will explain to you that with the example. So we have three examples here. The first example shows that how do you create a new thread with the function code but without passing any parameters to it, right? So you don't pass any parameter to the thread function, but you just create a new thread using the thread function, right? So let us look at that example first. So this is my main function, right? And this is my main thread, right? So I'm printing the thread id here at the beginning of the main function, right? So as I mentioned that this is a process and also a thread. The default thread will be running within that process. Now in this thread, in the main thread, I want to create a new thread, a child thread. Okay, so I'm going to use a pthread create function. This is the variable thread id which is declared over here. It is going to be the return value. That's why I have to provide the address of that. So the address will send the memory address to the operating system, which is where the new thread id, once the thread is created, the new thread id value will be placed over here. So this variable will give me what is the new thread id that I have used, that I have created. So in my parent thread, I can actually get the thread ID of the child thread using this. Okay. We don't want any attribute for the thread to pass. So I'm just going to use a null value. The third argument is the function, right? So I said that we have to pass the function address where the thread will kick off. The new thread will start from. Okay, so this is my function declaration. This is my function definition. Sorry. So in my function definition, right, I have basically said that this is the signature of my function. This is the heading of my function, and the heading of the function has to be exactly like this. You have to have the void pointer as the return type. You have to have a void pointer as an argument, and you have to have the function name. So this is exactly how you should always declare your function when you want to use that function for creation of the thread. So we are creating a new thread by using this function, okay? And now in this function, I am not passing any argument, right? So again, I have fourth value as a null. So fourth argument is a null, second argument is a null, first argument is going to be the return value of the thread ID, and this is the function which is going to be running as part of the new thread, as part of the new thread. Now what I'm doing is I'm sleeping for 1 second here because I want to make sure the thread is created and the thread function gets completely executed before my main thread finishes. Before my main thread finishes, right? Why? I'll come to that later. And then the last line, I'm just going to print again the thread which is completing. And so you can see that in my thread function, all I'm doing is I'm printing the thread ID of the new thread or the child thread here. Then I'm just doing this. I'm basically using these two variables and doing the summation of these two numbers. I'm printing the summation, and then I'm just printing that this particular thread is exiting. So this is my child thread code, and then this is my main thread code. Okay, so this is how the two threads can be created within the same process. All of this is still the same process. Okay, all of this is still the same process, not a different process. So let's run that code and see how it works. GCC minus pthread and thread no example no parameter dot c minus o thread example no parameter dot out. Okay, and now I'm going to run thread example no parameter dot out. So you can see that this is my main thread. The main thread ID is this one, and you can see that this ID is different than this ID because this is my child thread. So my main thread started, it created a child thread. Now the child thread is also running in a separate core, okay, which has this particular ID. The child thread is doing the summation, the child thread exited, and then the main thread exited. Okay, why main thread exited later than the child thread is because I put this 1 second sleep. If I don't do that, the problem with the threading environment is that the process will terminate when the main thread terminates. The process will terminate when the main thread terminates, and therefore the child thread will also terminate automatically. The child thread will not even get a chance to start. Okay, the child thread will not get a chance to start. So when I run this code, let me recompile again. So when I run this code, you don't see child thread code at all, because the main thread started, and before actually the child thread was created and allocated a different core, the main thread exited. And when the main thread exited, the process completed, process terminated. When the process terminates, all the threads terminates within the process. Right? So see, this is the difference. I mean, when you have the child process and the parent process, even if the parent process terminates, child process can be inherited by the by the init process, and so the child process can continue to run. But in case of threading, that is not the case. In case of threading, if the parent thread finishes first, right, then the child thread is not going to be inherited by anyone, because the whole process finishes, and because all the threads are part of the same process, all the threads will be terminated. That is how it works here. There is another way to fix this, but I'll come to that in the subsequent slides, right? So this is one example for starting the thread without passing any parameter. Now let us look at an example where we are passing one parameter. So the whole code is same, except you can see that I have a parameter as an integer value, and the fourth argument, instead of using a null value, I'm actually passing the address of the parameter. So the parameters in the thread functions are always passed by reference. Okay, parameters in the thread functions are always passed by reference, and there is only one parameter that you can pass at a time. Okay, so in this case, we have one parameter which has a value of 10, and the address of that is passed over here. Now, inside the thread function code, you can see that I'm declaring this pointer, right, star num2, and then that is going to be saving my void pointer. So basically, this is nothing but a typecasting, right? This is nothing but a typecasting for the integer pointer. And then I'm going to use that integer pointer value, right, integer pointer value to do the summation. So this is how you can actually pass the parameter to the thread function. Now the question is that we are only allowed to pass one reference, one address, right, to this function as an argument. But what if there are more than one value I want to pass to the thread function? What if I want to do that? The only way is create a structure. Okay, so create a structure. The structure has whatever number of arguments you want to pass to that thread function, and then you can actually pass. So you create a structure, you assign the values to each member, and then you pass the address of the structure. Okay, you pass the address of the structure. So this now void pointer is going to become the address of the structure and not the address of the integer. Okay, so that means you can now take the address of the structure or point. You can declare a variable with the address of the pointer variable for the structure, and then you can assign your reference to that. So again, you basically do the typecasting, and then using your local pointer variable here, you can then access the members of the structure and do whatever you want to do with that. Okay, so this is how you can pass the parameters to single value parameter or multiple value parameter to the thread functions. Okay, and as I said, this is how you can create the thread. So the main thread and the child thread, right? We'll look at more examples as we, in the next lecture, to see how more complex code can be created using the multi-threading environment. Okay, but it's 1:15, so let me stop here. If you have any questions, I can answer them, or else we will stop. Any questions from anyone? Okay, so if there are no questions, let me stop here, and I'll continue in the next lecture. I hope everyone has formed the project groups, and I hope everyone is finalizing their project titles, because we need to really start working on the projects by beginning of April. Okay, thanks everyone.